An important tool for calculus is to be able to manipulate expressions into different forms. Some of them are not going to be ones that you're normally would choose to do. Others are going to be, just a matter of simplification. So what I'm going to do here is I'm going to be comparing these, and at least 2 out of 3 of these, if not all 3 of them, are equivalent to each other. So what I'm going to do is I'm going to look at the simplest version, which is this one. And I'm going to try to change these all to 2 to some power to see if they're similar. So for example, this next expression, I can think of this as 2 to the first. So I can rewrite that by moving that to the top as 2 to the negative first. And then this second quantity, using my properties of exponents, I can multiply these two together and make that 2 to the 3x, because I have a power raised to a power. At this point, I have to think of my other exponent rules. For example, if I take x squared times x cubed, I get x to the 5th. When I have like basis, I add the exponents together to get my 5. So similarly, I would keep my base of 2 and add my exponents together to make that 3x minus 1. So that one and that one are for sure equal to each other. Now, using the same concept for my third quantity, I'm going to change all of these to base 2. So this is 2 to the 3x plus 1, and this is 2 to the 4th. Now, I have some other options, but just to kind of emphasize this, I can move this one to the top to make that 2 to the negative 4th. I have a 2 to the positive 4th already, and I have 2 to the 3x plus 1. And just like I did here, keeping my like bases, I can add my exponents together, negative 4 plus 4 plus 3x plus 1. And those two are going to sum to 0, and I get 2 to the 3x plus 1 instead of minus 1. So definitely not equal. Similar, but not equal to each other. Something that is not always accepted easily in lower levels such as Algebra 2 is the number e. E by definition, if you take e to the first on your calculator, you get about 2.71828. It's just a number just like the number 7 or anything like that. If you want, in calculus, they look at the idea of e as an approximation to this quantity as n approaches infinity. In other words, if you let the exponent n get extremely large and this division get extremely large, n is 20, n is 50, n is 100, n is 1,000, n is equal to 1,000,000, this quantity as a whole should get closer and closer to the number e, or to the number 2.71828. So grab your calculator if you haven't already, and enter that expression into your calculator. And then under Y2, put the number e to the first. Find your e to the x button, type in e to the first. There's also an e button. I want you to get in the habit of using the e to the x. Type that in and graph. And you should see graphs that look similar to what you see here. Now, you will find that we have a horizontal asymptote right through the center of this graph, and that graph is e. So in other words, as x approaches infinity or x approaches negative infinity, which is going this direction, either way, we get closer and closer to the line y equal e to the first, or y equal 2.7. So as x gets extremely, extremely large, we get closer and closer to the value e. Okay, a third thing that we're going to look at right now is working with exponents and what's called the one-to-one property. Now, one-to-one property is actually a pretty simple idea. For example, in simplest form, if I said a to the third equals a to the x plus 5, then you could say that x plus 5 has to be 3 because they have like bases. We can not divide out their bases or anything like that. It's basically focus on those exponents instead, and you could find that x equals negative 2. So the idea of one-to-one property says that let's try to get a common base and then ignore those bases. So to express that, I'm going to try to find the value of x in this equation by changing everything to a common base. Now, I see a 5, and if I think about 125, I want to see if I can think of it as 5 to some power. So I know that 5 times 5 is 25, and 25 times 5 would be 125. So I can think of this as 5 to the third. This is 5 to the first on the left. If I move it to the top, I have 5 to the negative first inside, raised to the x plus 1. So this is similar to our first problem. We were trying to get that common base. Now, our exponents rules say that I need to multiply those together, so I'm going to distribute and make that 5 to the negative 1x minus 1 power equals 5 to the third. Now that I have the common base, one-to-one property says that if I have like bases set equal to each other, then the exponents have to be equal. So I can say negative 1x minus 1 equals 3. Add 1, I get negative 1x equals 4. So therefore, x would be negative 4. Now, just to show you that this is true, let's take 1/5 and let's substitute in our negative 4 right there. That would be 1/4 to the negative 4 plus 1, which is negative third. Now, let's carry our exponents through just to practice some exponent rules. That's 1 to the negative third over 5 to the negative third. And if I wanted to emphasize the idea of negative exponents can be rewritten in terms of positive exponents, I can move those quantities, 5 to the negative third to the top to make it 5 to the positive third, 1 to the negative third to the bottom to make that 1 to the positive third, and I would indeed get 125 over 1 cubed, or 125. Now there's several other ways that we could arrive at that same conclusion, but that's a quick way that we can verify or check that we have a correct solution. The last part of our focus today is going to be working with some application problems, specifically with compound interest and continuous compounding. Compound interest is your typical formula that they use a lot for loans. When they're, for example, going to buy a car loan, they use a variation on compound interest and annuities to help arrive at payments. And the idea of compounding is if you had 12 times a year to emphasize a monthly payment, that would be 12. If you had daily interest that was added onto an account, then n would be 365. If you add that, say, monthly, you'd have n as 12. If you had it weekly, you'd have n as 52, etc. On the other hand, continuous compound interest, literally, if you could have the number of times that interest is added onto an account, if you could let n from your earlier formula approach infinity, you would have continuous compound interest. So essentially, as the number of times per year they calculate interest increases, it approaches this formula. So it's the same idea. If you recall from our earlier discussion, we had a similar notation to this, and we said that that approximated E. So ultimately, we arrive at a variation of that earlier idea. So to see this in a practical sense, let's look at some application problems. This particular problem, let's suppose your parents decided on your day of birth they were going to put $25,000 into a trust fund. It's going to pay 8.25%, and you want to figure out the balance on your 26th birthday. And you're trying to compare different ways of compounding. So quarterly would emphasize that you'd have n times per year where n equals 4. And so we would use our formula P times 1 plus R over N to the NT power. And if we actually substitute, P represents our principal or the amount invested. So that would be 25,000. Our 1 represents 100%. The R is an interest rate as a decimal, so 0.0825. And that's split up into 4 times per year, so n is 4. I'm splitting that, literally dividing that interest rate up. And then I'm going to take that to the power of NT. So I've got 4 times a year for 26 years. At this point, since I know everything on the right side of that equation, I can use my calculator and I can plug all of these values in, making sure that I get the 4 times 26 either in parentheses like so, or I make that 104 as my exponent because 4 times 26 is 104. So either way should work. Take a second, fill that into your calculator, see what you get for an estimate. You should have found approximately $208,941.65 as your total. That's an excellent investment of an original $25,000, and you end up with a lot more money. Okay, the next formula we're going to look at is the continuous compound interest formula, which is what we often refer to as the PERT formula, PE to the RT, where as n approaches an infinite times per year, we maximize the amount of interest that can accumulate at that same rate. So using this formula, we simply do our substitution. Principal, the original amount invested. E is a number 2.71828. We're just going to let our calculator do the work. R is still our interest rate of 0.0825 as a decimal. And then T is going to be the number of years, 26. Now this is where you need to be especially careful because that entire product is an exponent. So you're going to want to take special care to make sure you enter that in correctly. Take a moment now, see using your E to the X button, see what your calculator yields. So that time I ended up with about 213,000 and some change. So even though you're thinking, gosh, an infinite number of times per year calculated versus 4, This basically is going to maximize your interest if you keep it at 8.25% for 26 years. So this is the absolute most you're going to be able to earn in interest rate.